Hi, this is Mr. Hodgen, and this is the first semester final review for Algebra 2. Let's get started. How would the graph of the function y equals absolute value of x transform if the function were changed to y equals absolute value of x plus 4 minus 3? So what is the effect of these two values on the outside here to the graph y equals absolute value of x? Okay. Now, what you've learned throughout the whole semester with transformations is that it does not matter what the actual function is. So if this was x plus 4 to the second power and minus 3, the answer would still be the same. The plus 4s on the inside do the same thing to every graph. So, of course, absolute value is a v-shaped graph, right? And x to the second power is a parabola. They will transform in the same exact way. It's just that the shapes of the graph are different. Okay, just to look at this, we can look right here and see, well, if we change our h so it's positive 4, right, we see it moves the graph 4 to the right. Right now the vertex is right here at 0, 4, and if we make the k value negative 3, right, it moves it down. So as I mentioned before, it would not matter what kind of actual shape of this graph it is, and the transformation would be identical. So we can write something like uh, graph will translate looks like 4 to the left and 3 down. Okay, number 2, let's compare the graph of absolute value of x to the graph of 2 times the absolute value of x. So in a similar question, what does this number do to the graph? Not that it's inside the absolute value or after, but before the absolute value. Does the 2 in the graph cause g of x to be compressed or stretched vertically? So we know it's going to move it vertically, just which direction. So if we have our general absolute value, let's say that's our general absolute value, compressed would make it look like this. Okay, looks a little wider. Stretched would make it look like this, so it'll be taller vertically. Okay, so what will that 2 do to this graph? Will it make it wider or compressed or taller, skinnier? All right, if you need to, let's look at the graph again. And let's change the value in front and make it a 2. So from a, let's make that equal to 2. And you can see that is definitely stretched vertically. So the smaller this gets, you see it gets compressed when this gets smaller, but as it gets bigger, it becomes stretched vertically. So we can say that g of x is stretched vertically. There we go. All right, now let's do a little bit of solving with absolute value. And we're going to solve it 2 ways, graphically and algebraically. It doesn't matter which one we do first, just a personal preference. So let's see here. We are going to, looks like, move our vertex down 5. So let's go down 5. 1, 2, 3, 4, 5 from 0, 0. And here, this number acts as our slope. So we're going to go up 2 over 1. There we go. And good idea to use a straight edge here. And finally, let's graph y equals 3. And that's just a horizontal line going through 3. There we go. So our two answers, looks like, are going to be x equals 1, 2, 3, -4, and then 1, 2, 3, +4. Those are our two x values. So how do we get that algebraically? So we have to solve this by doing the normal operations on both sides of an equation. All right, first add 5 to both sides. All right, so now we have 2 times the absolute value equals 8. And then we can divide both sides by 2. So now we know the absolute value of x is going to equal 4. Right, so we know we're getting closer. We have 4. But how to get the -4? So remember, absolute value does two things to the number. So if it's a positive number, right, if you take the absolute value of a positive number, you get that same positive number back. If you take the absolute value of a negative number, you still get a positive number back. So that's why we have two answers when we have absolute value, because there's two numbers we can plug in for x that will give us a +4. So we can simply go here and say, well, because it's absolute value, x will equal -4 and x will equal +4. The absolute value of both of those numbers equal +4. So that way we can get the same answer graphically here and algebraically here. Right, we'll just do several more of these to get some good practice in. So let's look at number 4. Let's do this algebraically first this time. So I'm going to write this out. Here, -1 equals -2. And just like before, we'll go through and we'll do a little addition and multiplication on both sides. So we can add 1 first. So -1/3 times x plus 1/4. Absolute value will equal -1. We can multiply by the reciprocal here, so we'll multiply by -3/1. Right. Here we go. So these -1s cancel out, equal 1. 3's cancel out, equal 1. So just left with the x plus 4 and absolute value equal to -1 times 3 divided by -1 is +3. Right, and now, as we mentioned before, there are two answers that will give us a +3. So we know x plus 4 is equal to -3, right? But x plus 4, when is that equal to +3? Two possibilities. So if we solve each one of these individually separately, by subtracting 4 on both sides, we'll get both answers. There we go. So we have x equals, looks like -7, and then x equals -1. So two answers, -7, -1. All right, now that means we expect when we do the graphing that somewhere along x equals, right, here's the x-axis, here's -1 on the x-axis. This is where we expect somewhere on this line for our two graphs to intersect, at -1 and also at -7. Same thing here. Just so you know why these have the same answers here. So we can expect that these answers will show up right here. So here we go. Let's graph this. This means +4 on the inside means it's going to, vertex is going to move left 4, and this -1 means down 1. So from the center here, origin, we're going to go left 4, 1, 2, 3, 4, and down 1. Now the slope here is negative, meaning it's going to open down. So I want to go down 1 over 3. So down 1 over 3. Do that a few times. Down 1 over 3. You can already see where these are going to intersect probably. So here's my absolute value graph right there. Okay. Lastly, let's look at y equals -2. So y-axis is right here. Go down to -2, and that'd be straight across at -2. And just as predicted, our two graphs intersect at these dotted red lines because we already knew that's where they would happen because of the algebra over here. So it's confirmed that at -1 and at -7, our two graphs intersect. So for sure, these are correct. There we go. Let's go to number 5. And slight change here. You'll notice we go from equations on 3 and 4 to inequalities on 5 and 6. We have greater than or equal to, and then we have a less than over here. So let's graph this one first. So we have to go, let's see here, to the right 2 and up 3. So we can go right 2 and up 3, transform this, right? Where there's no number in front here, our slope, we're just going to use +1 over 1. Okay, so up 1 over 1 in both directions. So there is our absolute value graph. Let's get a straight line here. There we go. And here we're going to do y equals 6. So go 1, 2, 3, 4, 5, 6. There we go. And the question is, where is this greater than 6? So where does this graph become greater than 6? So it looks like from here, this is where it starts being greater than 6, right? This is 6 right here. Greater than would be the same as above. So this line starts being above the 6th line here and here, right? Now we just want to know for what x values, not where the actual graph is physically above. So another way of looking at it is from this x value and to the right, you can see that's where the graph is above this line. Same thing over here. This absolute value graph is above the 6th line for all of these x values, starting here, which is at -1, and every x value less than -1 to the left here will be above this value. Same thing over here. This is x is 1, 2, 3, 4, 5. So everything greater than 5, this graph will be above the 6th line. So graphically, we could put this down here and say, this is -1, all values from -1 and to the left, and then at 5, all values of 5 and to the right. So this is x is less than -1, or x is greater than or equal to +5. And that's all from the graph here. And we can get the same answer algebraically just like before. Okay, so we have absolute value of x minus 2 plus 3 greater than or equal to 6. And like before, let's add subtract to both sides. Here we go, subtract. So we have absolute value of x minus 2 is now greater than or equal to 6 minus 3 is 3. And like before, we can have a positive and a negative, right? So we'll get two solutions here. X minus 2 minus 2, right? And that's going to be a negative 3. Now the sign here, since I have a negative here, also flips. So it's going to go from a greater than equal to less than equal to. Similar to when you divide both sides by a negative, you flip the sign. Since we have this negative involved here, we are flipping the sign. And then we'll have our other inequality here, where everything stays the same. We didn't flip either sign, the negative or the inequality. And then lastly, let's go ahead and add 2 to both sides. So we have x is less than or equal to negative 1. Good. That one matches here. And x plus 2 here. X plus 2, we got x is greater than or equal to 5. So this one matches here. So of course, our answers should match whether we have a graphing method or an algebra method. We should be getting the same two answers. And for safe measure, we can put the or between them as well, because the graph goes one way or it goes the other way. All right, so let's do one more with number 6. So this time, let's solve algebraically first. Doesn't matter which one we do first, we'll get the same answer. This one has a coefficient out front, so I'll have to do one more step compared to the last one, but still start in the same place. You'll notice on all 4 of these, I started with subtracting whatever number is after absolute value. I started with that, adding or subtracting there. So here we have 2/5 times the absolute value of x plus 4. It's going to be less than 2. And then second, if there is a number here, we can multiply by its reciprocal, 5 over 2. 5 over 2. So 5's cancel out equal 1, 2's cancel out equal 1, left with just the absolute value of 4. And that's less than, here the 2's cancel out, so we're going to have 5. All right, let's separate these two. We have absolute value, and it's going to be less than 5. So I'm going to have two answers. We're going to have, when is x plus 4 greater than negative 5? So both signs change. This is a positive, so I flip both of them for the first one. And then also, when is x plus 4 less than 5, where they both stay the same? Subtract 4 on both sides. So when x is greater than negative 9, and here, when x is less than 1. So graphically, here's negative 9. So greater than negative 9 is this direction. And here's positive 1, let's say right here. So less than 1 will be right here. So you can see these connect. And you'll see that when we start off with a less than, the graphs end up connecting. So this means all the values between negative 9 and 1. We can write that two ways. We can say this is an and. So all the numbers bigger than negative 9 and they're also less than 1. Or we can write an in-between statement and say all the values from negative 9 to positive 1, like this. So this is okay, and this is acceptable as well. Two ways of writing these types of answers. With OR functions, like we saw in number 5, there's only one way to write them, and that's how we did when we did that problem. So let's go ahead and graph this now. So I'll graph this one in blue. I'm going to go left 4 and up 5 from the origin. So left 4, 1, 2, 3, 4, up 5, 1, 2, 3, 4, 5. There's my vertex. And my slope here is going to be up to right 5. So up to right 5. And up to left 5. And draw that line. Let's get that straight line here. And there we go. Okay. Oh, there we go. Okay, and we have, let's see here, 7. So we have 1, 2, 3, 4, 5, 6, 7. There we go, right here. So we can see that we predicted that the answer is all the values between -9 and 1. And then here on the graph, if we go to our x-axis, and here's -9, right? And here's one of the intersections, and here's +1, where the other intersection is. And you can see this graph, the absolute value graph, is below or less than 7 for all the values between -9 and 1. So we'll get the same answer either way. All right, let's move on to number 7. Okay. Still absolute value, but we're going to be talking about domain, range, and end behavior. All right, so let's graph this. We have, let's see, no left or right translation, but we have a vertical translation of 4. We're going to go down 4. 1, 2, 3, 4. And then our slope here is +1/2, so we'll go up 1/2. There we go. Just a few of them. There we go. We'll use that. All right. And what is the domain of this function? Meaning, what direction will this graph go on to? Is there any restriction? Can it stop anywhere, or will it just keep going forever and ever? And as you can see, left and right, domain is kind of what happens on the x-axis. Range is what happens on the y-axis, up and down. On the x-axis, if we look just on the x-axis, it looks like this will just keep on going right forever, and this will keep going left forever, which means our domain is going to be just from -infinity to +infinity. Right? Now, there's two ways of writing domain and range. I'm going to write them both. Another way of writing would be like we did before in absolute value. We're going to say the x values can go from -infinity to +infinity. Okay, these mean the same thing. And our range is going to, let's see here. Looks like this graph is going to keep on going up forever, but not down, right? It seems to start right here at the vertex and then it goes up. So the smallest y value possible is going to be right here, which is -4. So we're going to start at -4, and then it's going to go up forever to +infinity. Now, notice I used a bracket here because it's actually equal to -4. We can equal -4, but then when we go up to infinity, infinity is always going to be marked with a parenthesis. Another way of writing this would be -4 will be less than or equal to y for range, and then less than, just a regular less than, to infinity. Okay. And end behavior. Okay, so here's the end behavior. As x goes to infinity, what does y do? F of x. Well, in this case, it will be g of x that they gave us, just a different letter, doesn't change anything. G of x approaches what value? And then again, as x gets smaller, goes to negative infinity. What does the y do? Or the g of x do here? So basically, look at, for the top answer here, we're looking for one number or a positive or negative infinity for both of these. And to answer that, the top row here is looking at the right side of the graph. Since this is positive infinity, this is positive infinity. We keep on going forever. So it looks like this is going to keep on going up. So this is going to be positive infinity. And same thing on the left-hand side for the bottom here. As x gets very, very small, keeps on going this direction forever and getting smaller and smaller, the y value is still going to be going up because this arrow seems to be going an upward trend. So both of these are going to be positive infinity. All right, let's move away from absolute value and start doing some quadratics. So we can tell because we have a to the second power, no more absolute value signs. All right, so we know since it's a positive and it's to the second power, my graph is going to be a parabola. Okay. Now to find out all these different pieces of information, we're going to have to do several things. Okay, the first one we'll do is actually the y-intercept, because we can tell just by looking here that 3 is a y-intercept. So when it's in this format, the y-intercept is usually given to us. So we know the graph will cross at 3. Somewhere on the graph, nowhere special, just somewhere on the graph will be 3. To find the x-intercepts, that's when we have to go through and actually factor, right? We have to write this in factored form with the parentheses. All right, so we have to find what two values will multiply to 3 but add to 4. And pretty quick we can come up with 3 and 1. These add up to 4 and multiply to 3. And if you want to check to see, well, how come that is the right answer for this, you can always multiply these back together and you'll see x times x gives us x squared. X times 1 gives x, right? We want 4x, but the very next multiplication is 3 times x, so we get 3x. So we have a 1x and a 3x, that's why it's 4x. And then lastly, 3 times 1 is 3. So this does indeed equal this. If you're ever not sure of what you're getting here is actually the right answer, multiply it back together, make sure it equals what you started with. Okay. And since we're finding x-intercepts, right, that's right here across this line, this is where y is 0, right? Y is equal to 1 here, negative 1 here. The x-axis is where y equals 0. So we set this equal to 0. Meaning, when does x plus 3 equal 0? And when does x plus 1 equal 0? Right? And we'll get two answers. X is negative 3. X is negative 1. So our two x-intercepts are negative 3 and negative 1. So negative 1, negative 3, negative 2, negative 3. Which means our axis of symmetry must always be in the middle, right? Must be in the middle of your x-intercept. So what number is in the middle of your x-intercepts? You should come up with x equals negative 2, right? So some here, down here, the middle of this x-intercepts is our vertex somewhere. So our axis of symmetry is always the first coordinate of the vertex. That's the x-coordinate, right? And we just need to find out, well, where is the vertex exactly, right? And we can plug negative 2 back in to our equation here to find out what is the y value. Now you can plug it into the factored version or the standard form. Either way you will get the same answer. So if I plug -2, right, in the standard form here, I will get 4 minus 8 plus 3. 4 minus 8 plus 3 equals -1. Now also, if I plug -2 into here, if I plug -2 into here and here, right, and add 3, and then here add 1 to it, we'll get 1 times -1, which also equals -1. So it doesn't matter which form you plug it back into. But we do know now that my vertex is at -2, -1 right here. And we can see that our graph will go like this, right? And then because of this y-intercept, I also know I'll have a similar point right here on the other side. So I'm going to draw it on the other side as well, and then draw the graph. There we go. And there is my parabola. All right, let's go to number 9. All right, finding the roots. Now, let's do a little vocab here. The roots are the same as the x-intercepts that we just found graphically on the last problem. Same as x-intercepts, also called zeros. Also called the zeros. So we do not have a C term. We have the A term, B term, but no number on the end here, which makes it a little bit easier to solve by factoring. So what we're going to do first, like always, is take out a GCF. Now a 9 comes out of both of these, so I'm going to divide by 9. But there's also x in both of them, so we're going to also take out an x. All right. Now factoring is the reverse of distributive property. So we're just doing distributing backwards, right? So 9 times what will give us 9x squared, right? You'll come up with an x. 9x times x gives us 9x squared. And then repeat, 9x times what is 27x? And you'll get plus 3. So just the reverse of distributive property, you can always check as you're going along just to make sure you're doing it right. And just like before, once we have it factored and it's equal to 0, we can just separate them into two equations. Right? When is 9x equal to 0, and when is x plus 3 equal to 0? Solve them individually. We'll get, well, x equals 0 and x equals -3. So our two answers would be 0 and -3 here. Let's take a look at number 10, also by factoring. So as I mentioned before, first step is always GCF. So is there a number that 4, 20, and 25 all are divisible by? And let's see here, 4 goes into 20, but 5 is only divisible by 5. 5 goes into 20, but 5 doesn't go into 4. So you have to check all these combinations to make sure that you exhausted every possible number. So no GCF here this time. So we'll have to do a couple different methods if you want, but there's also a shortcut if you can spot it, and I'll talk about that at the end. But if you're not sure about the shortcut, what you normally do is go through and say, well, what two numbers multiply to the product of these, a times c, so that'd be 100 x squared, but they add up to the b value, 20x. Give that a moment, and you'll probably come up with just 10 and 10, 10x and 10x, right? So we can rewrite this as 4x squared, and then instead of 20, we're going to write 10 plus 10, 10x plus 10x. So all of this was just to rewrite this trinomial into a 4-term polynomial. So 4 terms instead of 3 terms, because in 4 terms we can do the factoring by grouping. So look at just the first two and do the same thing before, just with 2 terms. What's the GCF of the first two here? So with 4 and 10, right, we have a GCF of 2. 2 is the biggest number that goes into both, and then both have an x. So we're going to take that out as well. And reverse the distributive property, 2x times what is 4x squared, and 2x times what is 10x, and we'll get 5. Right, now when we're doing factoring by grouping, we just do what I just did here twice. So we did on the first 2 terms and the second 2 terms. The one caveat is that the part that's left over in the parentheses here has to be the same over here. These need to be identical. So I'm just going to go ahead and write that in, and then find the missing number that makes it equal to the 2 terms above. So 2x times what gives us 10x, and then 5 times what gives us a 25. And it should be the same number, right? In this case, 5, right? 5 times 2x is the 10x, 5 times 5 is 25. All right, so we have our 2 GCFs. That will make one of our factors, 2x plus 5. Our second parenthesis will be whatever this came out to be, and you just write it one time. Now, I mentioned before there is a shortcut, and you'll notice the shortcut exists because these are actually the same thing. That's usually not the case. Okay, so if you can pick up on earlier that the 4x squared is the same as 2x quantity to the second power, 2x times 2x is 4x squared, and that 25 is 5 squared, you can probably put together that the two binomials here are 2x and positive 5, 2x plus 5 and 2x plus 5. So that's the shortcut. All right, let's go to number 11. So let's complete the square, meaning we're missing a c value here for this particular polynomial. And we're asking ourselves, how can we write it in this format, right? This way we can take the square root of both sides and solve it that way. We could get the same answer factoring, but it's just a slightly different method. So in order to have the same value here, right, because it's going to be the same polynomial twice, we're going to need to take half of this value, which is going to be 5, and then square it, which gives us 25. And we have to add that to both values. Okay. And here we get 11 plus 25 is 36. So you saw I started by taking half of b, whatever this value is, writing it here, squaring it, right, writing that here and here, and then just simplifying both sides to give us this value. And now we can solve it by square rooting both sides. So we'll have x plus 5 equals plus or minus 6. So 2 answers when you do the square root here. So when is x plus 5 equal to negative 6? And when is x plus 5 equal to positive 6? And we'll get x equals, looks like negative 11 if we subtract 5 on both sides. If we subtract 5 on both sides here, we'll get x equals 1. So those are the two roots, negative 11 and 1. All right, let's try another. Number 12, same idea, let's complete the square. Now you notice we're starting off with the c value on the right-hand side, which is useful. So if it's not already equal to the C value, you can always subtract that or add that and move it over, because usually these start with equal to 0. So here we go. I'm going to rewrite this a little bit, set it up. So x squared minus 4x, right? And then some value equals negative 20. And then our goal is to write it this way so we can square root both sides. So we're going to have x here squared, leave a little space, and then equals. That's the setup. And to start off, we're going to take half of this value, right, negative 4. So half of that is negative 2. Square it, so that's positive 4. Add that to both sides, and we'll get negative 20 plus 4, which is negative 16. And we can square root both sides and solve. Now you'll notice we're going to end up taking the square root of a negative, right? So this means it's an imaginary number. So we'll have x minus 2 equals square root of negative 6. Well, square root of 16 would be 4 plus or minus. But with the negative, we'll have the imaginary I right there. So plus or minus 4i. And now when we solve, we'll have two roots, just like always. X minus 2 equals negative 4i, and x minus 2 equals positive 4i. Now, unlike when we have real roots, when we add 2 to both sides, normally we just combine these numbers. But 1 is real, the 2 is real, the 4i is imaginary. You can't actually write those as one single number or simplify them. They're two different number systems. So instead, we just write both of them with the real first. We'll say one of them is 2 minus 4i, right? So just rewriting both of these in order with the real first. And the other one would be similarly 2 plus 4i. And those would be our two roots. And you could just write those as 2 plus or minus 4i if you'd like to combine them. Right? Those are our two roots. There we go. Now, because this is imaginary roots, we are not going to be able to factor this if we tried, because we have those imaginary roots, and the graph would not have any x-intercepts. So if we don't have any real roots, it means there are no x-intercepts if we graph this. All right, now let's look at the third and final method, quadratic formula. So you need to have this committed to memory, that the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac, right, all over 2a. Now, the a, b, and c in the formula are just the numbers here by themselves. So 9 is a, b is 12, c is 9. And we just substitute those in carefully and do order of operations carefully. So we'll end up with negative 12, right? That's b, plus or minus square root of 12 squared, minus 4 times a, which is 9, times c, which is also 9. All divided by 2 times a, which is 9. So your first step is usually just plugging everything in, and then start doing some simplifying. And just be careful, try not to rush through it. Mistakes will happen if you go too quick. So we'll have negative 12 plus or minus square root of 12 squared is 144, and then 4 times 9 times 9, which is 324, all divided by 18. Right, so we end up with, it looks like, some imaginary numbers, and I can tell that because of the square root being a negative value. So this will come out to negative, looks like 180, right? Square roots of negatives always mean imaginary values. So we'll get over 18. Now the question is how to simplify the square root of negative 180. So what you have to do is, this won't be obvious at first, is find out what perfect square divides into 180. So 4, 9, 16, 25, 36, 49, 81, all the perfect squares, you're trying to see which one, the biggest one that divides into 180. So in this case, with a little bit of work, you'll find out that square root of 180 is the same as 36 times negative 5, with 36 being a perfect square, meaning you can take the square root of it, and then negative 5 over here to make negative 180. And that will take a little bit of time. So we'll have negative 12 plus or minus square root of 36, right, which is just 6, and then the square root of this negative 5, well, the negative will give us the I, and the square root of 5 we can't really take, so we just leave it as root 5. And that's all over 18. Again, that will take a little bit of time here to figure out what numbers work. So if I break it down one more step, I had the 36, right? I had the square root of negative 1, and then I have the square root of negative 5. And the square root of 36 gave me the 6, the square root of negative 1 gave me the I, and the square root of 5, I can't really take the square root of 5, so I left it as root 5. And that's how I got this right here. All right, we can also simplify a little bit more. If you notice that these real numbers all are divisible by 6, we can divide everything by 6. So I'm going to do one more step, divide everything by 6. So I'll end up with negative 2, right, plus or minus 6 divided by 6 is 1, so I'll just put I root 5. I don't need to put 1 I root 5, but just I root 5 is fine. And then divided by 18 divided by 6 is 3. And that would be the fully simplified answer. So this is one that's a little more intensive here, but enough practice, enough trials through here, you will get the hang of it. All right, let's look at one more of the quadratic formula. Okay, so let's plug this in. We'll have x equals, we'll use 1 for A, 4 for B, 13 for C. So we'll have negative 4 plus or minus the square root of 4 squared minus 4 times 1 times 13 times 13, all over 2 times 1, which is 2. So we'll have negative 4 plus or minus square root of 16 minus 4 times 1 times 13 is 52, all over 2. And let's just simplify that a little bit more. Negative 4 plus or minus root 30, negative 36, it looks like. So again, we have some imaginary roots. This discriminant, the part inside here, the square root is negative. Okay, so we have to look at, well, this one's a little bit easier compared to negative 180 on number 13. So negative 36, right, we can break that up into just square root of 36 times square root of negative 1, right, because these multiply to negative 36. Square root of 36 is 6, and the square root of negative 1 is I. So we'll just have plus or minus 6i. So we'll have negative 4 plus or minus 6i all over 2. And just like the last one, you can see how all of these are divisible by 2. So we can divide everything by 2. 4 divided by 2 gives us negative 2. 6i divided by 2 gives us 3i. And of course, 2 divided by 2 is 1, so we don't need to write over 1 though. So our two roots are going to be 2 plus or minus 3i. Again, with these being complex or imaginary roots, that means there are no x-intercepts. Okay, no real solutions. The solutions are complex instead. All right, let's look at number 15. Do a little bit of multiplying binomials here. So 12 times 12, and 12 times negative root 5. So 12 times 12 is 144. 12 times negative root 5 is just minus 12 root 5. And then, like, same thing here, we'll have root 5 times 12, so we're just going to add back the 12 root 5. And then root 5 times root 5, okay, is going to be 5. And it's positive times a negative, so this is just a negative. So the middle terms here, as you can see, end up equaling 0. A negative 12 root 5 and a positive 12 root 5, that equals 0. Cancels out. And we're left with 144 minus 5. So that's just 139. All right, lastly, for these types, we're going to do multiplying of complex. So these are kind of like the answers we're getting here, but we're multiplying them back together. So if you had the two answers for your quadratic and you want to find the original, we could do it this way. So 12 times 12 again, 144. 12 times negative I, it's just negative 12i. Oh, okay, yep. I times 12, positive 12i. And then I times I is going to be negative 1. Okay, I times I. Remember, I equals square root of negative 1. So I times I is just root negative 1 times root negative 1, which, like any other number, if you multiply a radical by the same thing, right, you just get whatever's inside. So root 2 times root 2 equals 2, root 6 times root 6 equals 6, and so on. Now, gotta be careful though, because this is positive times a negative, so we're actually subtracting a negative 1 here, right? So we have the i's canceling out, and we have 144 minus negative 1, so that gives us 145. There we go.